All right, class. Let's do some physics problems. Specifically, 2 through 12, at the beginning of Chapter 5. Doing some stuff about forces. Two horizontal forces act on a 2-kilogram chopping block that can slide over a frictionless kitchen counter, which lies in an XY plane. Don't you love physics problems? One force is, so I got F1 is 3I plus 4J newtons. Find the acceleration of the chopping block in unit vector notation when the other force is. So for part A, my F2 is going to be negative 3I minus 4J newtons. Well, that's easy. If I add those up, that's a whole bunch of 0. So the acceleration in unit vector notation will be 0. 0I plus 0J meters per second squared. And B, I've got the same 3I plus 4J newtons, but this time I'm going to add to it negative 3 positive 4. That'll give me 8J newtons. That's my net force. So force equals mass times acceleration. So acceleration is equal to force divided by mass. And what was the mass? It was 2 kilograms. So just dividing that by 2, that means my acceleration is going to be 4J meters per second squared. And for part C, the other force is 3 negative 4. So when I add the 3 negative 4, the sum of those forces is going to be 6I newtons. And then when I divide that by 2, my acceleration is going to be 3I meters per second squared. All right, that's pretty easy. Actually, that was very easy. Or are we kidding? Number 4. While two forces act on it, a particle is to move at the constant velocity of 3I. Somebody really likes their 3s and 4s around here. All right, so it's going to have that constant velocity. One of the forces is F1, which is 2I minus 6J newtons, and they want to know what is the other force. Well, if it's moving at a constant velocity, it doesn't matter what this velocity is. If the velocity is constant, then the forces must be balanced. So the other force would just have to be that to cancel that out. Because if an object is at rest or moving at a constant velocity, then the forces are balanced. And that's all there is to it. In a two-dimensional tug-of-war, Alex, Betty, and Charles, ABC, pull horizontally on an automobile tire. Sure, why wouldn't you? Okay, so the tire remains stationary. So we got to figure out what's up with these forces. So there's the force. That's Charles over there. Alex is over here. Do you think? Oh, never mind. And then Betty is down there. I don't think I've ever had... I've had students named Charles, and I've had students named Alex. I don't think I've ever had a Betty. Let's see. This is 220. And we don't know Betty's force, and this one is 170. And this is 137 degrees, so that means that this is 47 right there. All right, so kind of like in the force diagrams that we did, we can understand well what's going on here if we break things up into components. And I'll tell you, general rule for that is general rule for that is your XY axis system that you're going to use to break up your forces is just going to be your standard horizontal vertical, unless the object is on a ramp or like side of a mountain or whatever. So just because there are diagonal like forces that are not oriented along these, that doesn't mean that we should be picking axes that are all like in line with those. We should be doing horizontal and vertical unless the object is on a ramp. Okay, so I think like how do we proceed here? Well, I think I can take this and break that into its components. Let's do that first. 220 times the cosine of 47. That's about 150. And then 220 times the sine of 47 is about 161. Okay, well, if this thing's balanced, that means the verticals have to balance and the horizontals have to balance. And the only horizontals are this and this. Betty doesn't have any horizontal component to her force. So that means this has to be 150 here. If I've got 150 to the left, I've got to have 150 to the right, because I know that they're balanced. So if that's 150 and that's 170, I think I can find this by doing a little Pythagorean theorem, right? So this would have to be equal to the square root of 170 squared minus 150 squared, which is 80. And then in the up direction, I now have 161 newtons up, 80 newtons up. That's 241. So Betty must be balancing that with 241 newtons of force in the downward direction. And that's it. Number 8. A 2 kilogram object is subjected to 3 forces that give it an acceleration of -8.6 if two of the three rather, are F1, F2. Let's see, F1 is 3016. And F2 is -12.8. I'll find the third force. Okay, so I know that the sum of all forces is equal to mass times acceleration. And the mass of this thing is 2 kilograms. So 2 kilograms times this . That's my mass of 2 times the acceleration that they gave us. So I know that the sum of all forces must equal this. So I just have a little algebra. I don't know, does this count as algebra? It's kind of like arithmetic, I guess. So I just need to figure out what this missing piece. So it's like this is one side of the equation. I've got 30 minus 12 plus I don't know what equals negative 16. So this is, let's see, what is that? 18, and then I have to subtract that over to the other side. So it's going to be negative 34i is what we would need to have that total up there. You can write out that as an equation if you like. And then here I've got 16 plus 8 is 24 minus 12 is going to give me that 12. So the missing third force is this. And they didn't say magnitude and direction, so I think we could just leave it in its component form like that. All right. Getting the hang of this. Number 10, a 0.15 kilogram particle moves along an x-axis according to position as a function of time is negative 13 plus 2t, oh, I smell some easy calculus coming here, 4t squared minus 3 t cubed. With x in meters and t in seconds, in unit vector notation, what's the net force at time? .4, is that what it was? Yep. Okay, well, if this is the position, the velocity is 2 plus 8t minus 9t squared, and the acceleration would be 8 minus 18t. So the acceleration at 3.4 would be 8 minus 18 times 3.4. And then the net force would be the mass times the acceleration. So that is going to be 0.15 is the mass times negative 53.2, which is about 8 newtons in the negative direction. It's moving back and forth on an x-axis, so you could say that it's negative that in the I direction. Of course, if you only have movement along that one axis, there is no j direction. All right. Number 12. Oh, it's got 3 dots next to it. I'm scared. Just kidding, I'm not really scared of that. These little dots don't mean anything to us. It's just another physics problem. 2 horizontal forces, F1 and F2, they're both horizontal, act on a 4 kilogram disk that slides over frictionless ice on which an XY coordinate system is laid out. So these are 2 horizontal forces, but it's moving in an XY plane. Force F1 is in the positive direction of the x-axis and has a magnitude of 7. Okay. Force 2 has a magnitude of 9 newtons. And they're not telling us which way, but it's horizontal, so it's either this also this way or it's that way, one or the other. Figure 5.32 is a little graph there. Gives the x component, Vx of the velocity of the disk as a function of time during the sliding. They want to know what's the angle between the constant directions of the forces. Okay. I remember this causing confusion in the past. When they say 2 horizontal forces, they mean that the forces are directed like in that plane. So actually, I don't know about the direction of F2. I just know that it has a magnitude of 9. So it's like pointing off in some direction. I don't know. And I think it's totally confusing the way that they said that. So figure 5.32 gives velocity versus time in the x direction. So the slope of a v versus t is the acceleration. So it looks like the slope of this is, let's see, looks like it has a rise. I'm looking at the whole graph of, it goes from -4 up to 5. That's 9 over 3. So it looks like the acceleration is 3 meters per second squared. That is in the x direction. Okay, and what's the mass of this thing is 4 kilograms. So that means that the sum of all the forces in the x direction must be equal to 4 times 3 is 12 newtons. Right? So that means I must have there must be a component of F2 that is 5 newtons in the x direction. As if the sum of all the forces in the x direction, this one's all x direction, all 7, it's got to be getting some, remember this F2 is equal to 9 newtons. So exactly 5 newtons must be contributing to this. We got 7 from this one, there must be 5 coming from this. So I think now they want to know what the angle is. What's the angle between the forces? So since this one is horizontal, that would be this angle. If you're thinking to yourself, wait, how do you know it's not down here? Well, it could be down here. We don't know, but the angle between the two forces would be the same either way. So it looks like I need the, that's adjacent to this, so the cosine inverse of 5 over 9 is going to be equal to that angle. So let's see, cosine inverse 5 over 9 is about 56 degrees. All right, that's a pretty handy assignment there. Good job.